This is the beginning of section 6.3, and we're going to begin talking about something called volumes of solids of revolution. And this is actually going to carry us through both 6.3 and 6.4, so we'll be doing this for a little while. First thing we need to do is talk about what do we mean by a solid of revolution. I'm going to start with a simple graph. This is just the graph of y is equal to the square root of x between x equals 0 and x equals 4. So I've got this region defined between the graph and the x-axis. We already know how to find the area of this region. That was the last section. This section we're going to do something new with it. We're going to imagine taking this region and rotating it around the x-axis. So imagine this region coming forwards out of the page, rotating around all the way 360 degrees until it gets back to where it would start. Can you visualize that that's going to look something like this? This is what's called a solid of revolution. It's what we get when we take an initial region or an area in the xy plane and we rotate it around a line. In this case, the x-axis, although we can actually rotate it around any line. Our goal for this next several sections is to answer the question, how could we find the volume of that solid of revolution? Okay. Here's the technique that we're going to use. Like we've done a number of times before, when we're working with curved pieces, we don't usually have a nice geometry formula for them. Instead, we cut them up into little pieces whose formulas we do know. So in this case, imagine taking this whole shape again, right? This is, once again, the whole area that I was rotating around the x-axis. And I'm going to say, all right, I can't figure out the volume yet if I rotate the whole thing. So what if I imagine that I'm going to rotate just one little representative rectangle? Take that one small rectangle and imagine rotating that around the x-axis. What you're going to get is just this thin little disc, right? This circular disc. That I know how to find the volume of. That's really, technically speaking, a tiny little cylinder. If you imagine laying it on its side, it's a cylinder with a very, very short height. The height is the thickness of the disc. So I could figure out the volume of that cylinder. The volume would be the area of the circle, pi r squared, times the thickness or height of the disc. That's going to be our approach to these problems. So, as we just said, each of these thin little slices is almost a cylinder. It's really a thin little cylinder or a disc. Because of that, this method gets its name. We call it the disc method. And then if we took infinitely many of those little slices and let the thickness of each slice approach 0, we could treat that slices as a sum, basically, that we could add up and get the volume of the whole thing. Okay. Now, from geometry, we actually know the volume of each little flat cylinder or disc is pi r squared h. Again, h here, the height is really like the thickness of the disc. And so, if I imagine my original shape again, this was y equals the square root of x from 0 to 4. When I draw in the representative rectangle that I'm going to rotate around to create this disc, what are the radius and the height of that disc going to be? Well, the thickness or height of the disc is going to be this little piece right here, right? This delta x. Height, or we might think of it as the thickness. The radius of the disk is actually the height of that rectangle. And in this particular case, that height would be the y value, or square root of x. So, in our example, we'd have the volume, and I'm going to call this the volume of the disk. The volume of our disk, pi r squared h, is going to be pi times my radius, square root x, squared, times my height or thickness, delta x. That gives me the volume of just one of those slices, one of those disks. I need to add up infinitely many of them as they get infinitesimally thin to get the full volume all the way across this shape. And again, this is what we've really seen and defined as the definite integral. So the volume of my solid is what I'm going to get by adding all these things up, or in other words, integrating. Pi times square root of x squared is just x, and the delta x becomes infinitesimally small, a dx. In this particular case, my x values went from 0 to 4. And so I could pull the pi right out of the integral, and let's do this one by hand. We haven't done one by hand for a while. The integral of x would be x squared over 2, evaluated from 0 to 4. That would be pi times 4 squared over 2 minus pi times 0 squared over 2. 16 over 2 would make that 8 pi minus 0 for a final volume of 8 pi. So there we go. We have found the volume of our first solid of revolution. There's a nice animation online that I wanted to share with you. Let me bring that up. Here's that graph, y is equal to the square root of x. And when I start the animation, they're actually going to go through and essentially, in real time, show us everything that we just did. So I'm going to play this and we'll kind of talk along with it. First of all, they're going to actually show you that region being revolved around the x-axis. And then they're going to start looking at it, actually, I guess read graphing it here as more of a solid. And then they're going to start showing you the little disk that comprises the method that we just talked about. There's that one little disk that we're imagining finding the volume of. It's x units away from the origin, and there's the thickness dx. And then they're going to draw the radius in here in just a moment. There it is, the radius of the disk, you'll notice, is the y value, which in this case is the square root of x. So there we've got our pieces in that animated form. I'm going to pause this and we'll look at this in just a couple of minutes. All right, so that was fun. Let's try another one. I'm actually going to go back to the same graph that we had before. Notice here's that y equals the square root of x from 0 to 4. But this time, I'm going to go ahead and say, let's trap the region not below that graph, but above it and underneath y equals 2. So I've created a new region. Up here, between y equals the square root of x, and then this top line, which would be y equals 2. Okay. This time, I'd like to revolve my region around the y-axis instead. So I'm going to go around the y-axis. This time we're going to go ahead and watch the visual first. They used a slightly different function, but I just want to visualize the shape. And then we'll talk about our pieces to find the volume. So you can see they've actually already started here. They use 2 square root of x instead of square root of x, but it's the same idea, right? Oops. Sorry about that.
The washer method and the shell method are powerful results.
There we go. And you can see that shape kind of coming to life. All right, let's go ahead and come back to our shape. And I'm just going to sketch in here what happens when I rotate this. It comes all the way around, and I end up with this kind of a circular top and a pointed bottom, kind of like an old-fashioned top that a kid might play with, right? All right, once again, my goal is to find the volume of that solid. And this time, if I imagine a representative rectangle, when I'm going around the y-axis, I'm going to want to draw that representative rectangle horizontally. The reason for that is that horizontal rectangle becomes the radius of the disk when I'm revolving it around that y-axis. The thickness of the disk is going to be the dy this time, or delta y in my picture. Thickness or height of my disk. Delta y. And the radius, r, is actually an x value. Notice that if I took my function and solved it for x, x would have to equal y squared. So my radius this time is going to be x equals y squared. Right? So we've done what this said. We added a representative rectangle representing our radius and labeled it. And we're going to go ahead now and write the volume of that representative disk. It's really a cylinder, so its volume is pi r squared h. The radius was the y squared, and I have to square that. And the height or thickness is the delta y. So I'm actually going to get pi y to the 4th delta y for my volume. All right, that's just one disk. We'll have infinitely many of them, and we have to add up all of their volumes. We do that with an integral. So I'm going to integrate pi y to the 4th, and I'll let that delta y get infinitely small and become a dy. And y is my variable of integration, so the y values from the picture go from 0 to 2. I'm going to go ahead again, just integrate this one by hand. I've got the pi, and then that'll become y to the 5th over 5, evaluated from 0 to 2. Gives me pi times 2 to the 5th over 5, minus pi times 0 to the 5th over 5, and that'd be 32/5 pi, minus just 0. And there's the volume for that solid of revolution. All right, let's take a step back for a moment. We'll do some more examples, but I'd like to kind of create a general chart for us here, talking about this process. So this is kind of going to be our reference chart for using the disk method to calculate the volume of a solid of revolution. Okay. First of all, when does this method work? This is going to work as long as the region to be rotated sits right on the axis of rotation. You'll notice in both of the examples that we did, right, here, the region sat on the x-axis, which is what we were rotating around. And here, this region sat on the y-axis, which is what we were rotating around. If I wanted to take this region and rotate it around the x-axis, this region doesn't sit on the x-axis, so I couldn't use the disk method. We'll learn other methods for that, but it won't be the disk method. So disk method, it works as long as the region to be rotated sits right on the axis of rotation. No little hollow spaces are being created. The key to these problems will be finding the radius of the rotation, which is the length that begins at the rotational axis and extends to the outer edge of the area being rotated. This is really just the long side of the representative rectangle. So in a lot of words, this really just says the radius is the long side of the representative rectangle. This next piece is also really important. In the disk method, this radius, the radius of rotation, will always be perpendicular to the axis of rotation. So when you're setting things up and drawing your pictures, drawing your representative rectangle, notice in this problem, when we were rotating around the x-axis, my representative rectangle is perpendicular to the x-axis. In this one, when we're going around the y-axis, my representative rectangle perpendicular to the y-axis. So the representative rectangle that you draw must always be perpendicular to the axis of rotation. That's going to help your pictures a lot. All right. Let's do a couple of general ideas here. Rotating around the x-axis, and eventually we're going to extend this to other horizontal lines. For right now, I'm sticking with the x-axis. Let's imagine if we're rotating around the x-axis, we must have a region that sits on the x-axis. So I'll say that I've got some function y equals f of x between x equals a and x equals b. And we'll just say that this is the region that we want to rotate around that x-axis. Because we always draw our representative rectangle perpendicular to the axis of rotation, when we're going around the x-axis or any horizontal line, we'll always draw a vertical representative rectangle. Okay. That means that the radius of our disk is going to be the height of that rectangle. That's a y value, or f of x. Okay. The height or thickness of the disk is going to be determined by that little delta x, that little piece of the x-axis. And so the volume of my disk, pi r squared h, will just be pi times the radius, f of x squared, times the height, delta x. I can then integrate this from a to b. And that will give me my volume for my solid of revolution. All right, let's do a quick picture for going the other way. What if we would like to rotate around the y-axis which is what we're doing for right now. And again, a lot of what we say here will eventually extend to other vertical lines. This time, we're rotating around the y-axis. So let's assume that I start with some function, x equals g of y, between C and D. So it would be this region that I want to rotate around that y-axis. Since I am rotating around the y-axis, I draw my representative rectangle perpendicular to the axis of rotation. So this time it's going to make it horizontal. Here's the radius, the long side of the rectangle, and here's the height or thickness of the disk, the short side. Radius of my disk is the x value, which is g of y, whatever the function is. The height or thickness of the disk is that little piece of the y-axis, so that's going to be a delta y. And the volume of the disk, pi r squared h, will be pi times g of y squared times delta y. To add up all of those little disks, we integrate, and by this picture we'll go from C to D. And the volume of each little disk is pi g of y squared dy. So that's just sort of a general picture of these volumes of solids of revolution, once for the vertical case and once for the horizontal case. All right, let's go back to doing a few more examples. In this next problem, I'm going to let my region R be the region that's bounded by the curve f of x equals x plus 1 squared, the x-axis, and then the lines x equals 0 and x equals 2. Our goal is to find the volume of the solid obtained when we revolve R around the x-axis. So I'm going around the x-axis this time. All right. X equals 0 and x equals 2. X equals 0 is just the y-axis, of course. And x equals 2 would be the vertical line. I'm going to make myself a little extra space. I'm going to call this 1, 2, 3, 4, etc. And let's see, that's just a parabola that's been shifted to the left 1. So it would have its vertex over here at -1. And let's see, at 0, 1 squared would be 1. Let's see, I'm going to go just by ones here. 1, 2, 3, 4, 5. 9, 10. So 0, 1 squared would be 1. When x is 1, 2 squared would be 4. And when x is 2, I'd get 3 squared or 9. So there's half the parabola. The other half over here would just be symmetric. X equals 0, the y-axis, and x equals 2 over here. And then let's see. We're going around the x-axis, so the x-axis then forms my other boundary. And here's my region. We could have drawn this on a calculator, of course. I just chose to think it through by hand this time. It wasn't too bad of a picture to draw. All right, I want you to see if you can visualize, first of all. Imagine rotating that region around the x-axis. See if you can visualize what you're going to get. There's a nice little application, this is just a website, that's going to allow me to actually put some things in. It's going to visualize for me. Our function this time was x plus 1 squared. So I'm going to put that function in. And we wanted our region to go from 0 to 2. So I'm going to set that to be my function. And notice I've got a piece of it here. It looks like I need to fix my window a little bit. Let's see, that's up here. Let's go from I really just need the Y maximum to be bigger. Let's go up to maybe 12. There, now I can see it a little bit better. All right. Next, I'm going to rotate over here around the x-axis, which is the line y equals 0. And I'm just going to say revolve. Well, you know what? I need to fix my window one more time. Sorry. I need to go down further as well. Let's go negative 12 to 12. There we go. And now I can say revolve. And it's going to draw us that nice little volume of this solid of revolution. See if it kind of fits with what you thought it would look like when you visualized it in your head. It's a little slow, but it's coming around. Once it's done like this, I can actually grab it and spin it so you can see what that thing looks like. There we go. So that's our solid of revolution whose volume we're trying to find. In order to do this, the first thing I'm going to do is draw a representative rectangle. And remember, it always has to be perpendicular to our axis of revolution when we're using the disk method. So since x is the axis of revolution, I'm going to draw my representative rectangle perpendicular to the x-axis. The radius of my disk is the long side. The height of my disk is the short side. So, in this particular case, the height is a little piece of the x-axis. That would be delta x. The radius here is a y value, and the y value for this particular curve is x plus 1 squared. So the volume for my disk, pi r squared h, would be pi times x plus 1 squared squared times delta x, or pi times x plus 1 to the 4th times delta x. To get the volume of the entire solid then that I got, the one that we saw in the little application online, I would say, let's take this and integrate to add up all of the little disks that we would create. And this is an x integral, so the x values would go from 0 to 2. I'm going to go ahead and start integrating on the calculator just to make things a little bit quicker. One thing I will mention to you is when I use the calculator, just so that I can give an exact answer, I will often pull the pi out. And just do this part on my calculator. So 0 to 2 of x plus 1 to the 4th power, integrated dx, gives me 48.4, or if I want the fraction form, 242 over 5. And so if you do practice problems in your book, you'll often find the answers in the back will look like this. They'll give the answer in terms of pi to leave the exact answer. Now, of course, I could just take that and multiply by pi, and I can get an approximate decimal value as well. It's about 152.053, but that's an exact answer, and it's the one that the book will usually give to you. All right, a couple more. This time we're going to rotate the area that's bounded by y equals minus x squared plus 5 and the line y equal 1. And this time we're going to rotate it not about the x-axis, but about the line y equal 1. We'll then calculate the volume of the solid of revolution. So, here we go. We've got our y is equal to minus x squared plus 5. That's a pretty easy one to draw, right? That's just a parabola that's upside down and shifted up 5. 1, 2, 3, 4, 5. Like so. And then the line y equal 1. So this is my region. I'm probably going to want the intersection points here. They look like I could maybe pick them out, but I just graphed that by hand, so I should probably double check. You can either graph on a calculator, right, and get the intersection points that way, or just as a reminder, you can also do it by hand. This is a particularly simple one. If I just set the y's equal to each other, I would have 4 equals x squared, so x would be plus or minus 2. So this is the point positive 2, 1, and this would be the point negative 2, 1. Okay. Once again, you can always graph on a calculator as well. Whoops, I'm so sorry you couldn't see what I wrote down there. I intersected by setting the minus x squared plus 5 equal to the 1. Did the algebra to get 4 equals x squared, and x was plus and minus 2. Okay. And again, you can always graph with technology as well. Just a quick reminder that sometimes it's almost faster to do it by hand, right? All right, we want to rotate this around the line y equal 1. So we are rotating around this line right here, which is a good thing because now my region sits on the axis of rotation. If I was revolving around the x-axis, I'd have a gap, and that would be not okay for this disk method. Let's draw a representative rectangle. It's always perpendicular to the axis of rotation, so it'll be vertical, perpendicular to the axis that I'm rotating around. The radius is the long side, the height or thickness of the disk is the short side. So, I'm going to say here that the height or thickness of my disk is a little piece in the x direction. That's going to be a delta x. But let's think about the radius this time. The radius, this rectangle has its top at y equals minus x squared plus 5, but its bottom on y equals 1. So to get this distance here, I'm going to have to take top minus bottom, just like we did when we were finding areas in the last section. The top is minus x squared plus 5. Subtract the bottom, which is 1. So I actually have minus x squared plus 4. Okay. Again, you can kind of see the advantage of a nice picture. It really helps you to visualize the r and the h. The radius is always the long side of the rectangle. The height is the short side. So the volume of my disk pi r squared h is pi times the radius, negative x squared plus 4 squared, times the height, delta x. That means that the volume of the entire solid that I'll get when I rotate this around the line y equals 1 is going to be the integral of this. And I'm going to go ahead and pull the pi out like we did last time. And let's see, this is an x integral, so my limits of integration are x values. That means they'll go from this intersection point where x is negative 2 to that one where x is positive 2. Okay. And this is going to be the volume of, can you kind of visualize, it's almost like a lozenge shape when it rotates around. I went ahead and did this on the calculator, and when I did, I got 512 over 15. And so my final answer is going to be 512 pi over 15. And of course, if you wanted to, you could always get a decimal approximation for that. All right, couple more. In example 3, we're taking the region between the curve y is equal to 1 over x squared, y going between 1 and 4, and the y-axis. And then we're going to revolve that region around the y-axis and find the value. So I'm going to go ahead and, haven't used the calculator for our picture for a while. Let's go ahead and do that. Let's see. We want to take y is equal to 1 over x squared. And what's my window like right now? Let's see, let's go negative 5 to 5. And there it is. Now I really only want the part between 1 and 4. So I'm not even going to bother graphing the left-hand side. I'm just going to graph the right-hand side. And let's see, let's do it 1, 2, 3, and 4. And I'm just going to notice that when x is 1, y would be 1. When x is 2, I'm all the way down to a quarter already. When x is 3, I'm down to a ninth, and so on. So this gets really, really small here. And then we go up here. Oops, I got to go up a little farther, don't I? 2, 3, 4. So we're going from y equals 1 to y equals 4. There's y equals 1. There's y equals 4. And I want the region that's also bounded by the y-axis. So I'm looking at this. Okay, if I take that region and I want to rotate it around the y-axis, so we're going this way. You can kind of imagine again what that would look like. I won't graph all these just for the sake of time, but you can imagine kind of almost like a vase shape, wouldn't it, when it revolves around the y-axis, going around this way. All right, let's draw the representative rectangle. It has to be perpendicular to the axis of rotation. So it's going to go this way. R is the long side, H is the short side. So H, the height of the disk, will be that little piece in the y direction, delta y. The radius is actually an x value. It goes from left to right. And so I'm going to have to take my equation, y equals 1 over x squared, and I'm going to have to solve it for x. If I multiply the x squared over, x squared would be 1 over y, and x would be the square root of 1 over y. So the radius is x, or the square root of 1 over y. All right, volume of my disk, little thin cylinder, pi r squared h. In this case, the radius was the square root of 1 over y. We're squaring that. The height was delta y. So I'm actually going to get pi times just 1 over y. The square will cancel out the square root. Delta y. The volume of the entire solid of revolution, then, when we add up all the possible disks from top to bottom, we integrate. I'm going to pull the pi out, and I'll just get this 1 over y dy. It is a y integral, so the y values would go from y equals 1 to y equals 4. Let's do this one by hand. The integral of 1 over y would be the natural log of y, evaluated from 1 to 4. So I get pi times the natural log of 4 minus pi times the natural log of 1. The natural log of 1 is just 0. So that second term is going to be 0. Natural log of 4 doesn't come out evenly, but I could actually just leave my answer as pi ln 4, and then I would have an exact answer. Of course, I could also plug it in the calculator and get a decimal if I wanted to. All right. One more. In this last example, we'd like to find or rotate the region between the curve x equals y squared and the line x equals negative 2 about the line x equals negative 2. X equals y squared is just a parabola on its side, right? Sideways parabola. Again, if you needed to, you could graph it in Desmos if you have access to a calculator, or excuse me, if you have access to a computer, or by hand, you could just graph y equals plus or minus the square root of x. That's something you can do on a calculator as well. I'm just going to kind of freehand it though. I know this is going to be a sideways parabola with the x values being positive since they're y squareds. That's one of my curves. The other one is the line x equals negative 2. So this is x equals y squared, and this is x equals negative 2. And you know what? I did not give us enough information. We better add something here. Let's do this. Add this to the original problem, please. Let's go from y equals negative 1 to y equals positive 1. And let's see, I'm just going to call this negative 1 on the y-axis, and I'll call that positive 1. And that was just missing information that I should have given you. Otherwise, we didn't have a region, right? It was just an infinite space. Now that I've defined that, we've got our region, R. And again, this was y equals 1, and this was y equals negative 1. All right, we are rotating this around the line x equals negative 2. So we're going around this line, which is a good thing. That means our region sits on the line that we're rotating around, and it has to. Otherwise, we can't use this method. So I will draw my representative rectangle perpendicular to the axis of rotation. This way. Going around here, we're going to get kind of an hourglass sort of a shape, aren't we? The radius of each disk is the long side of the rectangle, and the height or thickness of the disk is the short side. So my height this time is going to be a delta y. And the radius, left to right, is going to be in the x direction. But because it doesn't sit right on the y-axis, I'm going to have to go right side minus left side. The right side is on the curve x equals y squared. Subtract the left side, which is on the line x equals -2. So my radius actually ends up being y squared plus 2 this time. And that means that the volume of my disk, so as a cylinder, pi r squared h, is going to be pi times y squared plus 2 squared times delta y. All right, the whole volume of the entire hourglass shape that we get when we rotate, the volume of the solid, then we'll get by integrating this. I'll pull the pi out of the integral again. And this is a y integral, so the y values would go from -1 to +1. Just as a reminder of a little trick for integration, maybe this hasn't come up yet, don't forget that when it's in this form, I actually can't integrate in that form. I would have to multiply this out in order to integrate this by hand. I'd have to write this as y to the 4th plus 4y squared plus 4 dy, and then I would be able to use my power rule. Now again, there'll be many times where I'll say it's fine to use a calculator to integrate, but let's practice this one by hand. That would be 1/5 y to the 5th plus 4/3 y cubed plus 4y from -1 to 1. And let's see, when I plug in 1, I'll just get 1/5 plus 4/3 plus 4 minus pi times, and when I plug in -1, that'll become a -1/5, a -4/3, and a -4. And I just pulled the pi out. I did everything else in the calculator, and this minus that gave me 166/15 times the pi. You can check that by integrating back at the beginning on the calculator as well. All right, that's the end of our discussion of the disk method here in section 6.3.